In Unit 8, we start to explore the second major idea that we're going to see in single variable calculus, the idea of the integral. And we'll see how this idea of integration, one of the main pillars in calculus, is going to be related back to the derivative ideas that we've already worked with through the last 7 units. We're going to introduce these ideas through the motivation of distance and velocity to start with, because these are two quantities that most of us have a reasonable intuition about. Let's remember that we've seen a relationship between distance and velocity before. If we call x our distance traveled and is a function of time, the velocity at any particular instant is obtained by differentiating x. So if we looked at dx dt, that would be our velocity as a function of time, our instantaneous rate of change of position. And we also had the graphical idea behind that if we had a graph of position, the slopes of that graph, the slopes of the tangent lines of that graph would give us the velocity values. Now let's turn that around and consider, what if we begin with a graph of the velocity instead and ask ourselves, how would we get the distance traveled from that graph? Let's take a look at a simple case. If we had a distance equals velocity times time, we know that already. Let's do an example here. Let's sketch it out with a couple of graphs here. Let's say we were moving at 5 meters per second. That was our velocity. And we did that for, say, 4 seconds. We know from basic physics calculations, or grade 9 science calculations, that the distance traveled, and let's make sure that we put that in here. The distance traveled is the velocity that we're traveling at, 5 meters per second, times the time we spend traveling, 4 seconds, and we would have a total distance of 20 meters traveled. All right. And that's great if we have a constant velocity. That's going to be one of the things we rely on here. Whoops. Sorry, I've got some new settings on the pens here. I'm just experimenting. So that would be a constant velocity calculation. The challenge occurs, or is going to be introduced, when our velocity is not constant. And in that scenario, this formula is not going to help us, at least not the way it does here. So we really do need an alternative way to think about this distance calculation that's not just velocity times time. One of the ways to get into that is similar to the way we related derivatives with calculational derivatives, or derivatives with slopes, by looking at the graphs. Let's consider the graph of this velocity against time, and here's that 4-second breakpoint. Where else would we see this multiplication on a graph like this? Well, multiplication happens when you take one distance times another distance, or you multiply them and get the area. Now here, this area is a little sketchy in terms of square meters or something like that, but if we take the properties of each of the axes, the units of each of the axes, 5 meters per second on this side and 4 seconds on this side, multiply out the units, we would get our 20 meters of distance traveled. So somehow it seems that this product idea can be visualized in a graph as an area. So when we're going from velocity down to distance traveled, somehow that seems to be related to an area on the graph of the velocity versus time function. And wow, I just can't write that today. All right, distance it is. Let's take a look and see how we would extend this further. Oops. There we go. So for a constant velocity, the distance traveled in a certain length of time is simply the area, in quotes here, of the rectangle underneath the velocity versus time graph. Now, there's that open question. What if the velocity is changing so we don't get a rectangular area on the graph? Well, let's say the velocity was much more interesting. Let's say the velocity looked more like something like this. That was our velocity, and that was time. Well, all of a sudden, area doesn't mean the same thing. I'm not sure even how we'd calculate the area right now beneath that curved shape. Let's see what we can do with calculus ideas, though. We can't determine the exact distance traveled yet. Let's put that in here. But maybe we can estimate it. So let's sneak up on the real answer. If we assume that the velocity is not changing too quickly, and over a short amount of time it's roughly constant, these themes should sound familiar, we would know how to find the distance traveled. Let's say if we zoomed in on, say, this interval here and brought that out, we would have the curve that stays roughly constant, and we would have a time interval here, and we would have a roughly constant velocity here. Well, then we could get back to our distance on this short interval is approximately velocity times time. Okay, so if we break it into intervals and look at small enough intervals, we get good approximations. And if we use lots of intervals to cover the time span we're interested in, we might get a good estimate of the entire distance traveled. And well, if we did that a whole bunch of times, what would we get? We would get a series of little areas that we want to calculate, and those areas would add up to the area beneath the graph. And here, most importantly, below the curved or non-constant graph of the velocity curve, of the velocity over time. Okay, so still, even though we're imagining the velocity changing, the area beneath that graph still seems like the thing we want to calculate if we're looking for a total distance traveled. All right, so that's going to be our inspiration to look at area problems more generally.